Okay, hello everyone. It's been a while. Been busy with work, but I'm excited to start reading this again. We're gonna be reading about the virtual file system. Always want to know more about VFS. So yeah, let's get started. The virtual file system. The virtual file system, sometimes called the virtual file switch, or more commonly simply the VFS, is the subsystem of the kernel that implements the file and file system related interfaces provided to user space programs. So basically, the interface the system calls. Okay, so all file systems rely on the VFS to enable them not only to coexist, but also interoperate. This enables programs to use standard Unix system calls to read and write to different file systems, even on different media, as shown in Figure 13.1. So basically, we have like two disks that actually are on two different file systems, X3 and ext4, or ext2. I keep saying ext4 because I see it so often. But anyway, so they implement these distinct file systems, but the implementation is an interface function defined in or declared in VFS. So what ends up happening is that the user space program will make a system call that's related to the file system to VFS, and then based off of the current file system loaded, VFS will make the appropriate function call to control the underlying file system correctly. So, common file system interface. The VFS is the glue that enables system calls such as open, read, and write to work regardless of the file system or underlying physical medium. These days, that might not sound novel, but we have long been taking such a feature for granted. But it is a non trivial feat for such generic system calls to work across many diverse file systems and varying media. More so, the system calls work between these different file systems and media. We can use standard system calls to copy or move files from one file system to another. In older operating systems such as DOS, this would never have worked. Any access to a non-native file system required special tools. It is only because modern operating systems such as Linux abstract access to the file systems via a virtual interface that such interoperation and generic access is possible. So basically what it's saying is that the VFS enables us to have a system that works with many different file systems. It doesn't matter what the file system is, as long as it implements those VFS functions. The VFS can call into them, and it'll feel like it's like it'll just be supported in this case, because it's the system calls that make calls to VFS, not directly to the implemented file system. So, new file systems and new varieties of storage media can find their way into Linux, and programs need not be rewritten or even recompiled. In this chapter, we will discuss the VFS, which provides the abstraction allowing myriad file systems to behave as one. In the next chapter, we will discuss the block I/O layer, which allows various storage devices, CD to Blu-ray discs to hard drives to compact flash. Together, the VFS and the block I/O layer provide the abstractions, interfaces, and glue that allow user space programs to issue generic system calls to access files via a uniform naming policy on any file system, which itself exists on any storage medium. The file system abstraction layer. Such a generic interface for any type of file system is feasible only because the kernel implements an abstraction layer around its low-level file system interface. This abstraction layer enables Linux to support different file systems, even if they differ in supported features or behavior. This is possible because the VFS provides a common file model that can represent any file system's general feature set and behavior. Of course, it is biased towards Unix-style file systems. You see what constitutes a Unix-style file system later in this chapter. Okay? So regardless, wildly differing file system types are still supportable in Linux. So if you have like a Unix style file system, it's going to be easier to support that as opposed to like, something like Windows NTFS or DOS FAT, but still it is supported. from DOS's FAT to Windows NTFS to many Unix style and Linux specific file systems. The abstraction layer works by defining the basic conceptual interfaces and data structures that all file systems support. Okay, so all the file systems have to support the specific, I guess, struct types that VFS demands. So the file systems mold their view of concepts such as this is how I open files, so an open system call, and this is what a directory is to me. To match the expectations of the VFS, the actual file system code hides implementation details. So it's like object-oriented programming. It's like implementing an interface. To the VFS layer and the rest of the kernel, however, each file system looks the same. They all support notions such as files and directories, and they all support operations such as creating and deleting files. So that's a common thing about VFS supported file system. They have to have this concept of a file and directory, and that's how it can be compatible. The result is a general abstraction layer that enables the kernel to support many types of file systems easily and cleanly. The file systems are programmed to provide the abstracted interfaces and data structures that VFS expects. In turn, the kernel easily works with any file system, and the exported user space interface seamlessly works on any file system. In fact, nothing in the kernel needs to understand the underlying details of the file systems, except the file systems themselves. For example, consider a simple user space program that does ret equals write, so write system call. Okay, so this system call writes the length bytes pointed to by buff into the current position in the file represented by the file descriptor fd. Okay, this system call is first handled by a generic syswrite system call that determines the actual file writing method for the file system on which fd resides. The generic write system call then invokes this method, which is part of the file system implementation to write the data to the media, or whatever this file system does on write. Figure 13.2 shows the flow from user space's write call through the data arriving on the physical media. On one side of the system call is the generic VFS interface providing the front end to user space, and on the other side of the system call is the file system specific backend dealing with the implementation details. The rest of this chapter looks at how the VFS achieves this abstraction and provides its interfaces. So here's user space making a write call, and really the system call is implemented by VFS, which then calls the real write method of the file system. And it's only the file system's job to actually do the real writing to the physical media. But notice how the user space doesn't really care about what the file system really is. It's really just the VFS that it calls here. Okay. So Unix file systems. Historically, Unix has provided 4 basic file system related abstractions: files, directory entries, inodes, and mount points. Okay, so files, directory entries, inodes, and mount points. So the 4, I guess we can think of it as 4 data structures. A file system is a hierarchical storage of data adhering to a specific structure. File systems contain files, directories, and associated control information. Typical operations performed on file systems are creation, deletion, and mounting. In Unix, file systems are mounted at a specific mount point in a global hierarchy known as a namespace. This enables all mounted file systems to appear as entries in a single tree. So mounted file systems kind of look like directories in this case. So contrast this single unified tree with the behavior of DOS and Windows, which break the file namespace up into drive letters such as C. This breaks the namespace up among device and partition boundaries, leaking hardware details into the file system abstraction. So it means that because DOS and Windows use drive letters, it becomes very tightly coupled with the specific hardware, versus in Linux, everything looks like another directory in this case. But for like DOS and Windows, if you have like an A drive, you kind of have to assume that that's like a floppy drive in this case. I'm not sure if anybody knows what that is nowadays. But yeah, like like an E drive with this could be like a CD drive, and you have to kind of really know these important like details. But with Linux, it's not the case. You just think of it as like a folder, another folder. You just need to mount that device as a folder. So, as this delineation may be arbitrary and even confusing to the user, it is inferior to Unix's unified namespace. A file is an ordered string of bytes, so just a chunk of data. The first byte marks the beginning of the file, and the last byte marks the end of the file. Each file is assigned a human readable name for identification by both the system and the user, so a file name. Typical file operations are read, write, create, and delete. The Unix concept of the file is in stark contrast to record-oriented file systems such as OpenVMS Files 11. Record-oriented file systems provide a richer, more structured representation of files than Unix's simple byte stream extraction at the cost of simplicity and flexibility. So in Unix, files are just blobs of data versus in like record file systems such as OpenVMS, files are literally like structured SQL rows in this case. You can think of it as like SQL rows versus in Unix, it's just like a chunk of data. So how do we organize that, right? So how do we organize this blob of data? So files are organized in directories. A directory is analogous to a folder and usually contains related files. Directories can also contain other directories called subdirectories. In this fashion, directories may be nested to form paths. Each component of a path is called a directory entry. A path example is /home /wolfman /butter. The root directory /, so this one here, the directories home and wolfman, okay, these here, and the file butter are all directory entries called D entries. So root directories, regular directories, and files are considered D entries. Okay, they're all called D entries, at least in this path. So when you break down a path, the file, the folder, and the root directory are all considered D entry types. So in Unix, directories are actually normal files that simply list the files contained therein. So they're just the same type of thing. It's just like a special form of file. Because a directory is a file to the VFS, the same operations performed on files can be performed on directories. Unix systems separate the concept of a file from any associated information about it, such as access permissions, size, owner, creation time, and so on. This information is sometimes called file metadata, that is, data about the file's data, and is stored in a separate data structure from the file called the inode. So file metadata are in what we call inodes, and these are special structs that contain file information. This name is short for index node, although these days the term inode is much more ubiquitous. So inode stands for index node, which makes sense. It's basically the file's metadata. All this information is tied together with the file system's own control information, which is stored in the superblock. The superblock is a data structure containing information about the file system as a whole. Sometimes the collected data is referred to as file system metadata. File system metadata includes information about both the individual files and the file system as a whole. Traditionally, Unix file systems implement these notions as part of their physical on-disk layout. For example, file information is stored as an inode in a separate block on the disk. Directories are files, control information is stored centrally in the superblock, and so on. The Unix file concepts are physically mapped onto the storage medium. The Linux VFS is designed to work with file systems that understand and implement such concepts. So not all file systems work with VFS, only file systems that have this type of metadata storing in inodes and other information stored in what we call the superblocks, and that's basically information about the entire file system. Okay, so non-Unix file systems such as FAT or NTFS still work in Linux, but their file system code must provide the appearance of these concepts. For example, even if a file system does not support distinct inodes, it must assemble the inode data structure in memory as if it did. So maybe this could also allude to the fact that NTFS on Linux is going to be slower because it doesn't have this concept of an inode. It has to kind of like reconstruct them in memory in runtime, most likely. Or if a file system treats directories as a special object, to the VFS, they must represent directories as mere files. Often this involves some special processing done on the fly. Yep. Okay, runtime. By the non-Unix file systems to cope with the Unix paradigm and requirements of the VFS. Such file systems still work, however, and the overhead is not unreasonable. So it's not that bad, I guess. VFS objects and their data structures. The VFS is object-oriented. A family of data structures represent the common file model. These data structures are akin to objects. Because the kernel is programmed strictly in C without the benefit of a language directly supporting object-oriented paradigms, the data structures are represented as C structs. The structures contain both data and pointers to file system implemented functions that operate on the data. So methods in this case will just be function pointers inside these structs. So the four primary object types of the VFS are the superblock object, which represents the specific mounted file system. So we have one struct just to represent what a superblock is. Then we have another struct that represents the inode object, which represents a specific file. Then we have another struct called the dentry object, which represents a directory entry, which is a single component in the path. So we had again something like A, B, oops. I'm going like on Windows mode. A, B, C. These here are D entries. Okay, A, B, and C, and maybe this one too, because that's a root. Okay. And the file object, which represents an open file as associated with the process. So note that because the VFS treats directories as normal files, there is not a specific directory object. Recall from earlier in this chapter that a D entry represents a component in a path, which might include a regular file. In other words, a D entry is not the same as a directory, but a directory is just another kind of file. Got it? So a D entry is not, we cannot say a D entry is a directory. But then at the same time, a directory is just another file. So there are two different concepts. A D entry is just a part of that path, something that represents a component of a path. An operations object is contained within each of these primary objects. So operations object is in all of these types of structs. Okay, these objects describe the methods that the kernel invokes against the primary object. So this operations object is embedded between these and every one of these, okay? And basically, it just contains all the function pointers to the methods required to operate on these individual struct values when they are initialized. So then we have the super operations object, which contains the methods that the kernel can invoke on a specific file system, such as write inode and syncfs. So this super operations object is going to be inside this superblock struct. And then you'll have the inodes operation object, which contains the methods that the kernel can invoke on a specific file, such as create and link. So this operations object is going to be in here. And then the dentry operations object, which contains the methods that the kernel can invoke on a specific directory entry, such as dcompare and ddelete. So this dentry operations object is going to be inside this struct here, this dentry object. And then finally, the file operations object, which contains the methods that a process can invoke on an open file, such as read and write, and which is going to be in here. So it just tries to be like an object-oriented pattern. Yeah, it's kind of interesting in that way. Okay, so the operations objects are implemented as a structure of pointers to functions that operate on the parent object. For many methods, the objects can inherit a generic function if basic functionality is sufficient. Otherwise, the specific instances of the particular file system fills in the pointers with its own file system specific methods. So here's the footnote here. People often miss this or even deny it, but there are many examples of object-oriented programming in the kernel. Although the kernel developers may shun C++ and other explicitly object-oriented languages, thinking in terms of objects is often useful. The VFS is a good example of how to do clean and efficient OOP in C, which is a language that lacks any OOP constructs. Yeah, one thing to remember is that C is not object-oriented at all. Okay? So again, note that objects refers to structures, not explicit class types, such as those in C++ or Java. So they are just the structs. So when we say objects in VFS world, we just mean the structs. These structures, however, represent specific instances of an object, their associated data, and methods to operate on themselves. They are very much objects. The VFS loves structures, and it is comprised of a couple more than the primary objects previously discussed. Each register file system is represented by a file system type structure. This object describes the file system and its capabilities. Furthermore, each mount point is represented by the VFS mount structure. The structure contains information about the mount point, such as its location and mount flags. All right. Finally, two per process structures describe the file systems and files associated with a process. They are respectively the fs struct structure and the file structure. Okay, so two per process. So every process gets these two structures, the fs struct and the file structure. Okay, so we have to remember that. Whereas the file system gets like these types here. Okay. And then the process gets these. So we will have many of these types of values for every process. So the rest of this chapter discusses these objects and the role they play in implementing the VFS layer. Cool. The superblock object. So that's like basically the information about the entire file system. The superblock object is implemented by each file system and is used to store information describing that specific file system. This object usually corresponds to the file system superblock or the file system control block, which is stored in a special sector on disk, hence the object's name. File systems that are not disk-based, a virtual memory-based file system such as sysfs, for example. So sysfs, procfs, like file system stuff that's coming or living all in memory. That's what it means, not disk-based. Generate the superblock on the fly and store it in memory. The superblock object is represented by struct superblock and is defined in linux/fs.h. Here's what it looks like with comments describing each entry. So this is the declaration of superblock. So I'm not going to go through all of this, but you can see like it has the definition of what is the block size, max file size for the file system type. Where's the operations actually? I'm curious. Export methods, super operations. I think it's here. Super operations, super block operations. Sorry. So struct super operations. That's consistent with this one, super operations. Okay. So the super operations is where all the methods manipulating a superblock object live in. Okay, so the superblock also has a list of inodes, so file system metadata, a bunch of other stuff. Okay. So the code for creating, managing, and destroying superblock objects live in fssuper.c. A superblock object is created and initialized via the alloc super function. When mounted, a file system invokes this function, reads its superblock off the disk, and fills in its superblock object. Okay. Superblock operations. So SOPs, super operations. The most important item in this superblock object is the SOP, which is a pointer to the superblock operations table. So this is what the super operations struct looks like. So it's a bunch of function pointers. You see that? So we'll have like things like was it alloc inode to allocate an inode given the instance of the superblock, right? We'll have destroy inode, dirty inode, we'll have write. So we have a bunch of stuff here. Okay, so this here is basically embedded. Where's it? SOP in here. So if you do like superblock, arrow, SOP, you'll basically get to everything here, and these are just functions. So yeah, so each item in this structure is a pointer to a function that operates on a superblock object. The superblock operations perform low-level operations on the file system and its inodes. When a file system needs to perform an operation on its superblock, it follows the pointers from its superblock object to the desired method. For example, if a file system wanted to write to its superblock, it would invoke this. So SB, which is superblock struct value, accesses the SOP property, which contains all the methods, and then the write super function, which is through a function pointer. So write super is going to be here, and that takes in the superblock itself. So this is how we get the this dot whatever in object-oriented programming. So it's instance of itself. So that simulates a this dot blah. Cool. So in this call, SB is a pointer to the file system superblock. Following that pointer into SOP yields the superblock operations table and ultimately the desired write super function, which is then invoked. Note how the write super call must be passed a superblock, despite the method being associated with one. This is because the lack of object-oriented support in C. In C++, a call such as the following would suffice: sb.writeSuper. In C, there is no way for the method to easily obtain its parent, so that you have to pass it. Let's take a look at some of the superblock operations that are specified by super operations. So then we'll have these basic operations here. For example, alloc inode creates and initializes a new node object under a given superblock. We also have destroyed inode, which deallocates the given inode. We also have dirty inode, which is going to be run by the VFS when we have a modified inode. So journaling file systems such as ext3 and ext4 uses this function to perform journal updates. And I think this one's obvious. You write an inode to the disk, drop an inode. I'm guessing that, let's see, well, we have destroy. Called by the VFS when the last reference to an inode is dropped. Oh, some links maybe? Normal Unix file systems do not define this function, in which case the VFS simply deletes the inode. Oh, okay, so it's not implemented in Unix-like systems. And then delete inode deletes the given inode from the disk. So what is this one then? Destroy, deallocates. What's the difference? Put super. So called by the VFS on unmount to release the given superblock object. The caller must hold the sloc block. Write super. Updates the on-disk superblock with the specified superblock. The VFS uses this function to synchronize a modified in-memory superblock with the disk. The caller must hold the sloc block. syncfs synchronizes the file system metadata with the on-disk file system. The wait parameter specifies whether the operation is synchronous. So, okay. So stuff in memory in the system to the real file system. Okay. So VFS stuff to physical stuff. The real file system stuff. Write superlock fs prevents changes to the file system and then updates the on-disk superblock with the specified superblock. It is currently used by LVM, the Logical Value Manager. Void unlock fs unlocks the file system against changes as done by write superlock fs. Statfs, called by the VFS to obtain file system statistics. The statistics related to the given file system are placed in statfs. Yeah, at least I'm familiar with this one. Remount fs, called by the VFS when the file system is remounted with new mount options. The caller must hold the slock lock. Clear inode, called by the VFS to release the inode and clear any pages containing related data. Umount begin, called by the VFS to interrupt a mount operation. It is used by network file systems such as NFS. All these functions are invoked by the VFS in process context. All except dirty inode may block if needed. Some of these functions are optional. A specific file system can then set its value in the superblock operation structure to null. If the associated pointer is null, the VFS either calls a generic function or does nothing depending on operation. So if you have any of these pointers pointing to null, VFS will just fall back to any generic operation. Okay. The inode object. The inode object represents all the information needed by the kernel to manipulate a file or directory. For Unix-style file systems, this information is simply read from the on-disk inode. If a file system does not have inodes, however, the file system must obtain the information from wherever it is stored on the disk. File systems without inodes generally store file-specific information as part of the file. Okay, so like NTFS FAT maybe. So in this case, for Linux, Unix, the files themselves, the file data is separate from the file information. So unlike Unix-style file systems, they do not separate file data from its control information. So that's the non-Unix style stuff. Some modern file systems do neither and store file metadata as part of an on-disk database. Whatever the case, the inode object is constructed in memory in whatever manner is applicable to the file system. So if you're working with the file system that doesn't support storing file metadata as a separate file, and then the file itself as like chunks of data, you're gonna have to implement inodes in memory, being built in memory. So the inode object is represented by the struct inode and is defined in linux/fs.h. Here's a structure with comments describing each entry. So another big list. So basically, I think what I'm interested in is finding the inode ops. So I'm guessing I_op. This one, inode operations. And then the associated superblock that the inode belongs to. Okay, makes sense. Oh, last access time, which is IA time, modified time, change time. Okay, I wonder which one is it, which file is associated with. Let's see. I guess there should be some sort of reference. Dentries. See, oh, user ID of the owner, the group ID. Okay, file size in bytes. I know some of these. Great. Okay. So we have all these information about the file itself. Cool. Oh, I guess the file itself is pointed to by file struct or dentry in this case. This is just information about it. Cool. Okay. An inode represents each file in the file system, but the inode object is constructed in memory only as files are accessed. But the inode object is constructed in memory only as files are accessed. This includes special files such as device files or pipes. Consequently, some of the entries in struct inode are related to these special files. For example, the ipipe entry points to the named pipe data structure, ibdev points to a block data structure, and icdev points to a character device structure. These three pointers are stored in a union because the given inode can represent only one of these, or none of them at a time. It's this one right here. Okay. It might occur that a given file system does not support a property represented in the inode object. For example, some file systems might not record an access timestamp. In that case, the file system is free to implement the feature however it sees fits. It can store 0 for IA time make IAA time equal to IM time, or update IAA time in memory, but never flush it back to disk or whatever else the file system implementer decides. Okay? So not every file system will implement certain things. So inode operations. As with the superblock operations, the inode operations member is important. It describes the file system's implemented functions that the VFS can invoke on an inode. As with the superblock, inode operations are invoked via, so here's a inode, iop, and then truncate method, or in this case, it's a function pointer. So in this call, I is a reference to a particular inode. In this case, the truncate operation defined by the file system on which I exists is called on the given inode. The inode operation structure is defined in Linux/fs.h. So here are all of the methods, which I guess in the next section, they're going to describe every one of them. Anyway, yes, I know the pattern now. Okay, so as I notice as we get later and later in this book, like the amount of interactivity is starting to decrease. I guess it's just the material is starting to become more dense. The following interfaces constitute the various functions that the VFS may perform or ask a specific file system to perform on a given node. So you'll have create, and it will take in the inode as like the this in a dentry mode, okay? So the VFS calls this function from the create and open system calls to create a new inode associated with the given dentry. So that's like pretty much the path. So the dentry object with the specified initial access mode, maybe read, write, things like that. So struct dentry lookup. So basically return back a dentry given some sort of inode and potential dentry. So this function searches a directory for an inode corresponding to a file name specified in the given dentry. Then link, invoked by the link system call to create a hard link of the old dentry in the directory dir with the new file name dentry. Unlink, called from the unlink system call to remove the inode specified by the directory entry dentry from the directory dir. Okay. Symlink, I know this one. Call from the symlink system call to create a symbolic link named symname to the file represented by dentry in the directory dir. Okay. So create this link to this place here. Make dir, we know this one. Called from the make dir system call to create a new directory with a given initial mode. Okay. So the inode and then the directory you want to create. Okay, armdir, created by the armdir system or called by the armdir system call to remove the directory referenced by dentry from the directory dir. mk node, I guess, called by the mk node system call to create a special file, either a device file named pipe or socket. The file is referenced by the device rdev and the directory entry dentry in the directory dir. The initial permissions are given via mode. Okay. Rename, called by the VFS to move the file specified by old dentry from the old directory, okay, to the new directory, okay, new dir with the file name specified by new entry. So renames are kind of like moves, essentially. Readlink, called by the readlink system called a copy at most bufflen bytes of the full path associated with the symbolic link specified by dentry into the specified buffer. Okay. Follow link, called by the VFS to translate a symbolic link to the inode to which it points. The link pointed at by dentry is translated and the result is stored in the name data structure pointed by ND. Not sure what that is. Put link. Okay, called by the VFS to clean up after a call to follow link. Sure. Truncate, called by the VFS to modify the size of a given file. Okay. Before invocation, the inode's size field must be set to the desired new size. Okay, that makes sense. And this is probably changing permissions of a file. Checks whether the specified access mode is allowed. For the file referenced by the inode, this function returns 0 if the access is allowed and a negative error code otherwise. Most file systems set this field to null and use the generic VFS method, which simply compares the mode bits in the inode's objects to the given mask. More complicated file systems, such as those supporting access control lists, have a specific permission method. Okay. Set attribute or set attra called from the notified change to notify change event after an inode has been modified. Okay. Get attra invoked by the VFS upon noticing that an inode needs to be refreshed from disk. Extended attributes allow the association of key value pairs with files. Set x attra used by the VFS to set the extended attribute name to the value on the file referenced by dentry. Okay. Get x attra used by the VFS to copy into value the value of the extended attribute name for the specified file. List x attra copies the list of attributes, okay, right here, for the specified file in the buffer list. Okay, remove x attra removes a given attribute from the given file. So I think these are all the chmod stuff, maybe. Okay, this is we call it list hell, right? So this is just go to the dentry. Okay, so as discussed, the VFS treats directories as a type of file. In the path/bin/vi, both bin and vi are files. Bin being the special directory file and vi being a regular file. An inode object represents each of these components. Despite this useful unification, the VFS often needs to perform directory-specific operations, such as the path name lookup. Path name lookup involves translating each component of a path, ensuring it is valid, and following it to the next component. So to facilitate this, the VFS employs the concept of a directory entry called dentry. A dentry is a specific component in a path. Using the previous example, slash, which is going to be the root, bin, and vi are all dentry objects. The first two are directories and the last is a regular file. This is an important point. Dentry objects are all components in a path, including files. Resolving a path and walking its components is a non-trivial exercise, time-consuming and heavy on string operations. So changing directories and listing them are actually pretty hard on the computer, which are expensive to execute and cumbersome to code. The dentry object makes the whole process easier. Dentries might also include mount points. In the path/mnt/cdrom/foo, the components /mnt, cdrom, and foo are all dentry objects. The VFS constructs dentry objects on the fly as needed when performing directory operations. Oh, wow. That must mean it has to be cached and things because there's a performance concern here. So dentry objects are represented by struct dentry and defined in Linux /dcache. Here's a structure with comments describing each member. Okay. So I'm looking for dops right here. Dops dentry operations. It has an associated superblock, subdirectories. So linked list to all the subdirectories. And I'm guessing since these are all dentries too, each one of these will also have their own subdirectories and so on. Okay. Unlike the previous two objects, the dentry object does not correspond to any sort of on-disk data structure. The VFS creates it on the fly from a string representation of a path name. Because a dentry object is not physically stored on the disk, no flag in struct dentry specifies whether the object is modified. That is, whether it is dirty and needs to be written back to disk. Dentry state. A valid dentry object can be in one of three states: used, unused, or negative. A used dentry corresponds to a valid inode. Okay, so it points to an inode. Inode points to associated inode. Yeah, I just said that. And indicates that there are one or more users of the object. The count is positive. A used dentry is in use by the VFS and points to the valid data and thus cannot be discarded. So you can't store a dentry. An unused dentry corresponds to a valid inode, but the VFS is not currently using the dentry object. Okay, so the count is 0. Because the dentry object still points to a valid object, the dentry is kept around, cached, in case if it is needed again. Because the dentry has not been destroyed prematurely, the dentry need not be recreated if it is needed in the future, and the path name lookups can be complete quicker than if the dentry is not cached. So maybe that's the reason why sometimes when we change directories or list them, they're slower the first time around, but then after a while they get faster. If it is necessary to reclaim memory, however, the dentry can be discarded because it is not in active use. Okay. A negative dentry is not associated with a valid inode. The inode is null because either the inode was deleted or the path name was never correct to begin with. The dentry is kept around, however, so that future lookups are resolved quickly. For example, consider a daemon that continually tries to open and read a config file that is not present. The open system calls continually returns inode, error no entry, I'm guessing. But not until after the kernel constructs the path, walks the on-disk directory structure, and verifies the file's inexistence. Because even this failed lookup is expensive, caching the negative results are worthwhile. Although a negative dentry is useful, it can be destroyed if memory is at a premium because nothing's actually using it. A dentry object can also be freed, sitting in the slab object cache as discussed in the previous chapter. In that case, there is no valid reference to the dentry object in any VFS or any file system code. All right, well, I think that's enough for today, so I'll stop. It's kind of not ending up what I thought it was. There's a bunch of list stuff, but oh well.